Hi, my name is Eric Martin. I'm the president and co-founder of MONSTR Sense Technologies, and thanks for coming by this talk. So I'll be talking today about ultrafast spectrometers for microscopy and imaging. To begin, let me give you a little background about MONSTR Sense Technologies. I founded the company with Professor Steve Cundiff in 2018. We are a spinoff of the University of Michigan. We license IP that he and I generated there at UM. Our expertise is in merging radio frequency electronics and optics, specifically ultrafast optics and laser scanning microscopy. And with, again, big lean towards that RF electronics. We spend a lot of time working on those. Now, what makes our ultrafast spectrometer special is that, unlike our competitors, it is fully collinear. Fully collinear means that all the excitation pulses are in the same beam. This requires state-of-the-art signal processing, but really comes with some huge advantages. So the single beam has the primary advantage that it is compatible with microscopy. Conventional ultrafast spectroscopies have pulses in different beams, meaning that the beams have to cross in the sample, right? So they are a non-collinear type of technique. This is not compatible with using a microscope objective. But if you have a system that is, so say a fully collinear one, then you can generate images. So say, for instance, using our laser scanning microscope that I'll talk about, we're able to generate ultrafast images, so scan the beam over and get decay maps as a function of position. Also, being compatible with microscopy means that you can focus the beam tightly, right? And this is great because this significantly reduces the pulse energy requirements. To give you a sense of scale, a typical ultrafast spectrometer is fundamentally limited to have a spot size of about 30 microns, whereas a spot size with your typical microscope, 20x objective is focused down to 1 micron. And so what this means is that you have a peak power requirement that's reduced by a factor of 1,000 by shifting towards using microscopy. What this means for you is that you can ditch your amplified laser and instead use a megahertz oscillator. Megahertz oscillators now with OPO technology and things are great at spanning the full wavelength range that you want to access from UV through IR. And so this is definitely a great alternative to the conventional ultrafast spectrometers using amplified lasers. Another thing that's great about having a single beam is that it's just easy to use. The non-collinear geometries get a lot more unwieldy, particularly as the techniques get more complicated with more than 2 pulses. And so yeah, with our software and the geometries, it's easy to keep the system aligned. It's basically remains aligned, and so it's easy to generate transient absorption 2D spectra plus. So what can you do with ultrafast spectroscopy? There are a lot of parameters you can measure, both electronic and vibrational. Highlight a few here. So energy and charge transfer are very popular to measure. Spin transfer, many body effects. Multidimensional spectroscopy is really one of the best ways to measure, isolate many body effects. Vibrational modes are very popular to measure with transient absorption spectroscopy. You can look at both acoustic and optical vibrational modes, measure the zero phonon line as well. Electronic and vibronic decay times, popular to measure. Again, with transient absorption spectroscopy, you can look at these time scales. And then for those of you who are interested in doing 2D spectroscopy, this is a great way to measure the homogeneous line widths of an inhomogeneous system. Even more than this, you can look at homogeneous properties in the presence of inhomogeneity. For instance, with 2D spectroscopy, you can measure a vibrational resonance that is much smaller, lower energy than the inhomogeneous line width. For a much longer list of applications, please check out our website, our resources page, monstersense.com/resources. There are a lot of samples that have been used or have been measured using these, transient absorption and multidimensional spectroscopy techniques. Many of these have also been measured using the same kind of technology that's in the Bigfoot engine. So they're capable with imaging. My background is in semiconductors, so if you come and talk to me, I'm going to talk to you a lot about semiconductors, but there are a lot of groups, and I've looked at a lot of papers where been very interested in a lot of the other samples that get measured. So I'd love to chat about those as well. So I got a few listed here. monolayer transition metal like chalcogenide, the monolayer similar to graphene, colloidal quantum dots, perovskites, been looked at a lot. Vacancy centers, actually there's a lot of inhomogeneity due to the environment. Vacancy centers you can pull out with multidimensional spectroscopy. Quantum nanostructures. Other samples, so there's a Jennifer Ogilvy's group at the University of Michigan has used the same technology in the Bigfoot engine to look at in vivo photosynthetic bacteria. They were able to distinguish 2 different flavors of those bacteria, which was really great work. I've cited there. Molecules unfolding those blobby spectra into multi-dimensions really helps with being able to understand what parts of the molecule, and the large molecules are close to each other, interact with each other. Cold molecules been demonstrated as well. Biological tissue, so stimulated Raman spectroscopy or stimulated Raman scattering imaging is commonly used to look at biological tissues, and our Bigfoot engine is capable of that as well. So we're talking about these applications. What really makes the Bigfoot spectroscopy engine work? And I say Bigfoot because that is our flagship product, is the Bigfoot Ultrafast spectrometer. Basically, the input is a pulsed laser. So that's a train of pulses comes in. We break that into four different arms that are each tagged using an acousto-optic modulator and delayed with respect to each other. So then we recombine these 4 beams into a single beam that has all 4 pulses with well-controlled delays between them. And again, each of these pulses is distinguishable by the frequency tag that we've applied to it over the pulse train of the laser. So after you consider several of these sequences, you can isolate any individual contribution of one pulse. For those of you that are more familiar with transient absorption spectroscopy or stimulated Raman spectroscopy, I like to sometimes call the first 2 pulses the pump and the second 2 pulses the probe. These are both just frequency shifted. And so if you overlap, for instance, A and B, they will modulate. They'll have an amplitude modulation as they interfere. And then if you overlap C and D, the same for the pump, probe. And you can imagine that then you now have 2 pulses that have an amplitude modulation on them. We split these into A, B, and C, D respectively so that we can then spectrally resolve these axes. But you can really think of it in the same way as the simplified pump probe measurement, just with these extra 2 pulses that give us additional useful information. Coming back to the Bigfoot engine, there is a reference laser in there with a 3 to 10 meter coherence length that measures the optical paths with interferometric precision. And so we maintain our knowledge of the relative delay of each of these pulses with better than 1 femtosecond resolution. We measure all these and all this in the time domain. So all these scans, and these are quick. The delay stages, we will scan these continuously as we're scanning one axis. And so we can measure these all in the time domain or Fourier transform that to measure in the frequency domain. Our measurements are made with phase resolution. We're measuring the phase and amplitude of all our signals all the time. And so we can get a spectrum or a time domain plot for each of these axes. Now, I said that we have these 4 pulses, and then I said that you could think of it as pump and probe. Well, why do we have these 4 pulses? To break this down a little bit, let's start with the simplest measurement, I think, in multidimensional spectroscopy, a 0 quantum, which is completely analogous. It's identical to a transient absorption spectrum. So in transient absorption spectroscopy, you have a pump pulse that's amplitude modulated. Here you can think of the first 2 pulses, A and B, as overlapping. So having a time delay of 0, and that's fixed. We would then scan the delay between second and third pulses. This would be the wait time in a transient absorption spectrum. And here's where you're going to have evolution of the population. Either it'll oscillate because of some vibration, or it'll decay because you're looking at a population decay. We would then also scan the delay between the third and the fourth pulses, and we would Fourier transform that delay. Right? And again, that scan happens very quickly. We're going to rapidly scan that stage continuously, map out the oscillation in the time domain, and Fourier transform that to get a spectrum. And so if you plot the spectrally resolved last final delay as a function of the wait time, you now have a transient absorption, a spectrally resolved transient absorption spectrum. And our software, our transient absorption spectroscopy software, really just plots that. You don't have to think about what's going on in the Bigfoot engine, but that's basically what's going on. What's great though, and the reason why we have all these pulses, is that there are other things that you can do. You can also spectrally resolve the pump. And so if you spectrally resolve the absorption and spectrally resolve the emission, as you would in conventional 2D spectroscopy, then you can get all kinds of additional information, right? You're now correlating the absorption energies with the emission energies, which lets you pull out those homogeneous properties. And there are other sequences as well for looking at other types of coupling. There's a sequence that exclusively pulls out many-body effects. If you're interested in these, please, I got my contact info down at the bottom of the screen. Please reach out. So, summary: each of these provides identifying and characteristic info about electronic and vibrational transitions, and each of these techniques can be distinguished by a frequency tag applied to all 4 pulses in the sequence. So there's a recent study that sort of highlights how to use this that was recently put on the archive, comes out of Steve Cundiff's lab, led by Torben Pers. And so they're using the technology in the Bigfoot engine to measure heterostructure of molybdenum diselenide and tungsten diselenide. And in here, it's common to look at, with photoluminescence, this interlayer exciton, which is these 2 layers, these 2 monolayers put right next to each other, electron in one, hole in the other layer, and they can bind to form an interlayer exciton. This has been measured with photoluminescence, but there's actually another type of interaction between these 2 layers called coherent coupling, where you have an exciton in each layer that interact through dipole-dipole interaction. These can be distinguished using 2D spectroscopy. So basically, you correlate the absorption and emission energies using 2D spectroscopy. And then what they did is they looked at those coupling peaks. So that's where you have absorption at one energy, emission at another energy. And they looked at how that evolved with the wait time, right? And so at short time scales, so under 100 femtoseconds, you can actually see an oscillation. That oscillation corresponds to coherent coupling. The decay corresponds to charge transfer. And so they were able to tease out what the coherent coupling timescale was, what the charge transfer timescale was. All that information was written in here into the data. So what does this engine into a packaged Bigfoot ultrafast spectrometer look like? Basically, it's this. So Bigfoot has a small footprint. It's 1 foot by 2 foot, shown here. Again, it's capable of all these techniques. If say you get Bigfoot to do transient absorption spectroscopy, we're going to provide you with software that's for transient absorption spectroscopy. You don't have to worry about the underlying things going on in the engine. But yeah, we have software that's for transient absorption, software for impulsive stimulated Raman scattering, and multidimensional coherent spectroscopy. The Bigfoot, it's an ultrafast spectrometer, has a single beam output. It's got the detector built into there. So actually the signal will either reflect off your sample, transmit through, come back into the Bigfoot. It has the detection, and then this comes with processing electronics as well. These systems are designed for 500 and 950 nanometers, or there's a blue Bigfoot for 350 to 500 nanometers. We also have an infrared one, goes from 950 to 1300 nanometers. We can also, with any of these, we can do 2 color. So that'd be the pump, the AB, and probe, the CD, have different colors. Please, if you're interested in that, reach out to me. We've also got an upgrade for this. If you want to do transient absorption spectroscopy of longer lived states that live up to 3 nanoseconds, we have a delay stage upgrade. It does increase the size of the box a little bit from 1 foot to 1.5. There's several detection variants. So though the standard is heterodyne detected, so basically the first 3 pulses will generate an optical 4-wave mixing signal emitted by the sample that then gets interfered with the 4th pulse on a detector. You can also do fluorescence detected, 2D, photocurrent detected. So if your sample's in a diode structure, photoelectron detected. There are all kinds of things you can do, because the signal is really just, it's a modulation. And so our electronics have a lock-in amplifier that we've designed built into it, with a wide dynamic range. You can put all kinds of detections into there. I mean, what it's going to do is it's going to look for the modulation of that nonlinear signal of interest. And so you can integrate our spectrometer with really any kind of detection scheme that you want to do, as long as it has some, population basis or electric field basis. So that concludes the ultrafast spectroscopy part. I have a couple slides just to talk about what we've been working on of late, which is our laser scanning microscope that we call NESI. Laser scanning microscope uses 2 galvos to rapidly scan the beam over a sample. We were looking at laser scanning microscopes on the market and didn't find one that really fit with what it is that we wanted to do. So we ended up here at MONSTR Sense building our own. And the things that we were particularly interested in is, one, we wanted to be able to work with cryostats and bulky sample holders. Conventional microscopes made for biologists with their slides really didn't cut it, because we have, some people want to work with samples that are heated or, again, in cryostats. And so we built this microscope that will actually move up and down. It's got this huge sample volume, so you can put a large sample holder and things underneath it. And the whole microscope actually has a range of 4 inches that it can move up and down to fit pretty much whatever you want in there. We also have a removable objective head, so that if you have a microscope objective built into your cryostat, that too can work with the NESI laser scanning microscope. The other thing is, none of the microscopes we saw in the market really did the XY galvos well. So they just put the galvos really close together, which does give you a little bit of aberrations, but more important for us was that the reflected beam has an offset. We put relay lenses between these 2 galvos. You actually use 2 parabolic mirrors to eliminate that reflected beam offset. Our optics are also designed to operate between 450 and 1100 nanometers. So if you have a laser spectroscopy system in your lab that you want to integrate with imaging, and you want to do it easily, please do reach out to us. This is designed to work in sort of custom applications in your lab. And again, we got this wide wavelength range, and we can design this for other wavelength ranges as well pretty easily. So if you're interested in this, please do reach out. Of course, we made it to work with Bigfoot, and NESI to work with Bigfoot, and to make another monster joke, when Bigfoot and NESI are merged, the resulting instrument is a beast. This lets us acquire ultra-fast movies in seconds. So basically, we can get an image and look at how that evolves in time. We can zoom in on regions of interest, both get higher spatial, higher spectral, higher temporal resolution. All these are just sort of software knobs that we can set and tune. This system, again, will also be coming out soon. Is a cool, exciting system we're really excited about. So if you want to get any more information about our instrumentation or ask a question about a specific application in your lab, please reach out to us at info@monstersense.com or reach out to me directly at emartin@monstersense.com. I look forward to chatting with you from our virtual booth.